Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 33, part C. We're going to complete the normal distribution discussion in this video. Last time we talked about the standard normal distribution. We started in on how to read a z-table, but we'll continue that in this discussion. So I want to remind you of the PDF of the standard normal is here, and it goes from negative infinity to positive infinity. It has a mean, so z is normal 0, 1, so that means that it has a mean of 0 and a standard deviation of 1, or a variance of 1, same thing. Z, the z-score, z equals x minus mu over sigma, is the number of standard deviations either above or below the mean by the score x. We call it a raw score x. So we're going to continue on with reading a z-table, doing some examples, and then we're going to show the relationship between the normal distribution and the chi-squared distribution. So let's look at our z-table and let's do some of these problems. We have find the probability that z is less than or equal to 1.24. Let's look at this table, and I want to point out in this table that the z values are on the edge or margins of the table. They're kind of outside of the table. So over here we have 1 decimal place, and across the top we have the second decimal place. Okay? And inside we have areas. So the same thing is true up here. Now I need to find the probability that z was less than or equal to 1.24. So I come down on this side, the first decimal place, and find 1.2, which is here, and I go across until I get underneath the 0.4. So I have 1.2, and then the second decimal place is a 4. So 0.8925 and 0.89, whoops, I always forget to turn on my pen, 0.8925. So this is phi of 1.24. All right, now I want to find the probability that z is greater than 1.24. So this is the same as 1 minus phi of negative, no, this is 1 minus greater than 1.24, yeah, so this is 1 minus phi of 1.24, that's right. And so I need to find phi of 1.24, and I look, so greater than, this is the same as phi of negative, so this is also equal to phi of negative 1.24, and so this and this are both in table VB, the second one, which is down here, and so I look up 1.24 here, and that's this value here, and see I have 1 minus phi of z, which is negative, a phi of negative z. So I can read that directly from this table by knowing that symmetry. Yep. So 0.1075. And then I made a mistake here, so I want to find the probability that z is greater than negative 1.24. And I can write that as 1 minus phi of negative 1.24, and I look up phi of phi of negative 1.24, which I did right here, which is, so 1 minus 0.1075 gives me 0.8925. A good way to check this is to draw a picture. So up here, here is negative 1.24, and I want greater than. So this is the probability that z is greater than negative 1.24 is obviously more than half, because here's 0. So it needs to be a big number. This is a big number, so it helps me confirm that I've gotten the right thing. So drawing pictures are very helpful sometimes. All right, so I want to now find the probability that z is between 1.24 and 2.37. I can rewrite that. I need to look at this and figure out how to do this within the confines of what I have. And so I've drawn a picture, and this is z, and I've marked 1.24 and 2.37. I've just estimated, so I have enough room to write it. I don't care about scale so much, except they're both positive. And so what I'm going to get looking at table VA or 5A is that I'm going to get this probability from all the way from 2.37 all the way down to negative infinity. But I don't want all that. I want to subtract off this portion that is below 1.24. So I can look up this probability in the table as well, and I can subtract the two to get what I want. So this turns out to be phi of 2.37 minus phi of 1.24. And so I go to table 5A, and I'm going to clear this out. Table 5A, and I look up 1.24. So here is 4, and that gives me 0.8925. And 2.37, and that is going to be over here, 0.9911. And when I subtract, always take the large number minus the small number because it has to be a probability. The result has to be, this is a probability, oops, it's a probability, so this has to be a positive number between 0 and 1. So 0.9911 minus this gives me the answer. Now, find the probability that Z is between negative 2.37 and negative 1.24. Here I was looking at the positive of the numbers. Now I'm looking at the negatives. And so again, I'm going to take the largest, which is now negative 1.24, phi of that, minus phi of the smaller one. Now I go to table 5B and look up, I look up 1.24 here and 2.37 here, and I'm subtracting them to get the difference. And when I do that, I see that I get exactly the same number that I got up here for the positive. And again, these are equal because of symmetry. Okay? So this number is equal to the same. Now, if I look at the difference between negative 2.14 and 0.77, this again is going to be phi of 0.77 minus phi of the negative 2.14. So I have to go to the two different tables. I have to go to 5A here, and I have to go to 5B here, and I can look those up. I'm hoping you can do that by now, but go check and make sure that you see these two numbers, and we subtract and we get this answer. Now, I've talked about critical value. I want to formally define it. The critical value is Z sub alpha, and that is this number, Z score, such that the probability that Z is greater than, not less than, but greater than Z sub alpha is equal to alpha. And so if Z sub 0.05, that's my Z sub alpha, so alpha is 0.05. So the probability that Z is greater than that number is 0.05. Okay. Of course, this keeps going forever. Never touches. All right. And that is phi of negative Z sub alpha. Okay. Now, Z sub alpha is the 1 minus alpha percentile. That's not easy for me to say anyway. So, so this is a percentile, the 100 times 1 minus alpha percentile. So let's find the 95th percentile of Z. And so I want the probability that Z is less than phi or pi of 0.95 is going to be 0.95. But I need, if that's the case, then I will have, let me erase this, I need Z sub alpha, okay, or this is Z sub alpha, or which I don't know, but it's going to be pi of 0.95. That means that 0.95 is over here, and 1 minus 0.95 equals 0.05 over here. So this is going to be, make this smaller. This is going to be Z of 0.05, which is pi of 0.95. Okay, and so if I want to find Z of 0.05, I go to my table, and it actually interestingly, is at the bottom of the first 5a, not 5b. See, here's my alpha and my z sub alpha. And if I find 0.05, then z sub alpha is going to be 1.645, which is what we have put right here. So now we're going to go to, we're going to look at the theorem, which we've already proved, but it says if x is normal mu sigma squared, then z equals x minus mu over sigma has a normal with 0, 1 distribution, so a standard normal distribution. And we did prove it earlier in this section. So here's a remark that goes with that. Let x be any distribution, any random variable of any distribution, with mu equals ex, and sigma squared equals e of x minus mu squared. Remember, that's the definition of the variance. Then the mean of z, I just plug in z for x, or plug in the value of z, and then I take the expectation. I can pull out the 1 over sigma using my property of expectation, linear operator, and then I can distribute the expectation, and e of a constant is the constant, and e of x is mu. We've just said up here, we defined. And so I've got sigma of mu minus mu, which is equal to 0. So the mean is going to be of the transformation, even though it may not be standard normal, the mean of the z transformation is always 0. And then the variance of z, the transformation for any random variable, is e of x minus mu squared over sigma squared. And I can pull out, this is a square here, so I can pull out the 1 over sigma squared, and I'm left with e of x minus mu quantity squared, and we define that as sigma squared up here. So I've got 1 over sigma squared times sigma squared equals 1. So the mean and variance, 0 and 1, it just may not be a normal if it didn't start as a normal, right? It'd be something else. So you can do that whenever 0 is in your range of your random variable. You can't do that if it's all positive or all negative or something. Okay, so let x be normal with 316. Okay, I want to find the probability that x is between 4 and 8. And so anything I do to any part of the inequality, there are 3 parts to this one, I have to do to all of them. So 4 minus 3, so I'm subtracting the mean. So that would be the first thing I would do. I do this part. And so I have to do it to all 3. And then I divide by the standard deviation. And when I do that, this gives me a z, which is here. And then this gives me this number, and this gives me the 1.25. And of course, that's phi of 1.25 minus phi of 0.25. I look those up in the table. I get this value. Please do that. And then I've got probability that x is between 0 and 5. And that's going to be, again, I subtract the mean from all 3 and divide by the standard deviation. I end up with these values, which is this, phi of 0.5 minus phi of negative 0.75. So I have to look in the 5b table for this one, and I get this. So verify that you know how to get these and that you can do this. Now I'm going to go to a little more complex case for most people, and I want to find this constant c such that this is true, such that the absolute value of x minus 25 is less than or equal to c, that probability is 0.9544. I'm going to use a definition of the absolute value. So absolute value of x is negative x if x is negative. It's positive x if x is positive. That's one way to say it, to kind of make it easy to remember, I hope. And so I have, so then when I use the break up or get rid of the absolute value, I have negative c, and then I have x minus 25 is between negative c and positive c. Now, I've already subtracted the mean. That's already been subtracted. I don't do that again to transform this to a z. X already has 25 subtracted. That implies that whatever this is, and whatever this is, has already had 25 subtracted from it. Don't need to do it again. But I do need to divide by the standard deviation, which is 6. So that's what we do, all 3 places. We end up with this, which of course gives us phi of c over 6 minus phi of negative c over 6. And then I can't solve for both of those. I need to rewrite this in terms of positive c over 6. And so I do that that is 1 minus phi of c over 6. Take the negative of the negative, I get a positive. These, don't forget this negative sign, these do not cancel out. It becomes 2 times that, and then minus 1. So distribute your negative sign correctly there. Just make sure you distribute that correctly. And so I get 0.9544. This is equal to 0.9544. I solve for this. I get this. I divide both sides by 2. I get this. I look in my table, inside my table, to find 0.9772. And here it is. And that means that I have a 2.00 is my z-score that goes with it. And so c over 6 is 2. C is equal to 12. Now let's do this very important theorem. I'm sorry I'm running late, but this is very important. We have to get it in. So the theorem is that if we have a random variable x that's normally distributed with mean mu, variance sigma squared, of course sigma squared is positive, then the random variable v, which is the square of x minus mu over sigma, so square of that, that's z squared. And the distribution of z squared, if z is a standard normal, is going to be a chi-squared with 1 degree of freedom. So here's the proof. We're going to set v equal to z squared, where z is a standard normal distribution. Then, since z squared here, v has to be positive, okay? So the CDF of v is going to be given, let's say, g of v. Probability v is less than little v. And then we're going to substitute in for v, which is z squared right here. And that's less than v. And so then I'm going to use the fact that absolute value of z is the square root of z squared, and the fact that these two are the same thing, right? So the square of z absolute value is also z squared. They give you the same thing. So I substitute that in here for z squared, and then I can take the square root of both sides, and I use the property of absolute values to have z between negative square root of v and positive square root of v. And that probability, this probability function, is the integral from here to here of my standard normal. And because of symmetry, remember this is a symmetric distribution, z is a symmetric distribution, that each half is the same, right? So mu equals 0. So the area over here is the same as the area over here. So I can, and it's the same for any value. So if I take negative square root of v over here and positive square root of v over here, the area between those two has to be the same as the area between those two. Okay? And so we multiply by 2. All right? And we change this bottom limit to 0. And so we have that. And then we're going to make a substitution. Let z equals the square root of y. In other words, y is equal to z squared. And then dz is given here. And we solve so z is equal to the square root of v, implies that z squared equals v equals y. And so we end up with v up here instead of the square root of v, making this substitution. And don't forget your 2. And then we substitute in what we're so we've got here and here, and we have that, and we do the substitutions that we came up with up here, and it simplifies to this distribution, this integral with respect to y, because y was our change of variable here for v greater than or equal to 0. And then we rearrange it, and we can see that we have separate these out. And then I'm trying to prove that this is a chi-squared with 1. So I'm going to try to make this look like something minus 1, because I have the chi-squared says r over 2 minus 1 in this exponent. And then I have the variable divided by 2, so theta is 2 up there. And so now I've made this pattern, the pattern of a gamma distribution. Note that g of v is 0 when v is negative. Oops, I hit the wrong thing. When v is negative. And the PDF of v is the derivative of capital G V, and that's using the fundamental theorem of calculus. So then we've got G of V is equal to this, and it's a PDF. And because it's a PDF, we know that this is equal to 1. So we're going to use that fact, and we're going to let U be V over 2. V is 2U, du here, dv here. We substitute in, remember that this is equal to 1. We make our substitution, and we do some cancellations after we do our substitution. And we move this out to the front, and we take a look at this, and we notice that we have a gamma function. So this is the gamma function, so we have gamma, and here is gamma of alpha, so alpha, oops, that's not very pretty. So gamma of alpha equals gamma of 1/2. That's what we have here. So this is gamma of 1/2. So I have 1 over pi, square root of pi, times gamma of 1/2. And so that has to be equal to 1. Here it is, down here. It has to be equal to 1. And that's not an equal to. That's a multiplied. So this is 1 over square root of pi times gamma of 1/2. That, solving for gamma of 1/2, gives me that it's equal to square root of pi. So this is something you want to write on your formula sheet. You may need it. So then we can go through this, and now that I know what the square root of pi is, I can rewrite the square root of 2 as 2 to the 1/2. I have v to the 1/2 minus 1, e to the negative v over 2. V is greater than or equal to 0. Now I can replace pi over 2 with the gamma of 1/2, and lo and behold, I have a chi-squared distribution, right? And r over 2, alpha, is equal to r over 2, which is 1/2. So r is equal to 1, and that means that v is a chi-squared with 1 degree of freedom. This is an important proof. Please make sure that you understand what happens in every step and that you could do this yourself. All right, so that's it for the normal distribution. Don't forget to scan and upload your lecture notes before midnight, the date listed on the course calendar. Update your list of distributions and theorems. If you have any questions, please come to virtual office hours. If you can't do that, email me, but email me a picture, 2 pictures, one of your work and the other of the problem, so that I can help you quickly through email. Stay safe, and we will see you next time.